of part 2. So he will complete a story about imaging through the atmospheric turbulence. How do we model that? And then in part, the second half of part 2, I will pick up, and then I will talk about how do you render turbulence on your computer. So basically, we're going to go into a simulation. Then we will talk about how do you simulate these turbulence effects really fast, so that you can generate a lot of images and to train your neural network. Okay, so that's the plan. So Nick, are you ready? Okay.
Okay, so I get 1/2. Let me see. I think I'm unmuted. Yeah. Okay. I think I'm good. I have to go here. All right. I think there we go. Okay. So yeah. So just to this time, I think we can go out of the meeting a little bit slower. So this is also, to be honest with you, I'd probably like this a bit more. But okay. So let's use some Fourier optics to describe this image. Okay. So I'm looking at this turbulent image, right? And what do I kind of see here? Okay, so I see, for one, spatially varying blur. Okay, in some places it's blurrier than others. I see some pixel shifting. So what do I mean by that? Basically, straight lines are no longer straight. They're kind of squiggly or something. Okay, it's varying with distance. That's not going to be too important for now, but it's something I noticed. Also, the amplitudes aren't too bad. So what I mean by that is it's not like random parts of the image are all of a sudden very dark or something like that. So basically this implies that, at least to me anyway, in sort of an intuitive level, that I'm not looking at any sort of complicated amplitude distortion. I'm primarily looking at phase distortions, okay? So everything we've talked about so far has basically assumed that we have a plane wave hitting our imaging system. So this is going to be, like let's just say a plane wave propagating through a vacuum. So in a vacuum, there's no randomness, there's no refractive index change, and the phases of the wavefront are not distorted. However, when I have this sort of, I like to think of it as denting up of the wavefront. Okay, so I think of the atmosphere as maybe sort of a distributed grid of little tiny hammers, okay, that are just slightly tapping on the wavefront as it propagates through. I end up denting up the wavefront, and when it lands on the imaging system, it's no longer going to go directly into the focal point. And why is that? That's because if I do my Huygens-Fresnel principle, I draw a couple of circles, all this kind of thing, I'll no longer get a spherical wave on the other side of the lens. I'll get still a dented up wave on the other side of the lens. And this will end up being a pretty nasty looking point spread function. So just to give you a little bit of background, this part maybe I'll go through a little bit fast, but just to give you a sense of how the index of refraction is modeled is we'll model it as 2 parts. One is we'll say that there's a mean value, okay? So as for the sake of argument, we'll just say 1, okay, maybe 1.01 if you really want to haggle me on that point. And then there's also some fluctuations that occur, okay? So we'll take R to be our spatial coordinates, T to be the time, lambda to be the wavelength. So technically, right, the index of refraction is dependent on wavelength. However, just for the sake of this talk, we're just going to focus on visible light, okay? So we'll kind of ignore the fact that it is truly wavelength dependent, which is decently justified, again, for the case of the visible band. I was going to try to bring up the chat here. I forgot to do that, but I'm stuck in the presenter mode, but that's okay. So anyways, all right, so continuing on. So now I want to ask, okay, well, what's the, oh, did I skip one? Okay. Now I want to ask, what's the autocorrelation function of the distribution of the indices of refraction, okay? So of course, the go-to thing would then be to ask, well, what's the autocorrelation, okay? Because if I know the autocorrelation, or if I know the power spectral density by virtue of the Wiener-Khinchin theorem, then I can pretty much describe the whole entire random medium, and then I can sort of begin my analysis, okay? So I won't tell you reason, at least at the moment. But so sadly, there really is no, at least analytic, autocorrelation function. Okay. However, Kolmogorov figured out by some way the power spectral density. Okay. So for a specific reason, as we'll see, you can never really take the power spectral density, get back to the autocorrelation function. But he sort of invents a different type of correlation function that we'll talk about in a little bit. That one you can have an expression for. So he ends up finding the expression for the power spectral density. There are a bit of extra slides, sort of to give you a sense of sort of his assumptions about turbulence, okay? But so basically it ends up just being this term here, k to the power -11 multiplied by Cn squared. Okay, so Cn squared is going to be really a big thing for the rest of the turbulence stuff. Cn squared is going to kind of be like the variance in some sense. It's going to basically map to the strength of the turbulence. A higher Cn squared will mean more turbulence, stronger turbulence, whereas a low Cn squared will mean low turbulence. Also to give you an idea of how small Cn squared is. Okay, so the fluctuations are incredibly small. A strong value for Cn squared would be 1 times 10 to the power of -14. Okay, so it's very, very small. That would be a strong turbulence. Weak turbulence would be like 10 to the power of -17 or something like that. Okay, so it's in that range of strength. It's an incredibly small sort of quantity. There's also the von Karman power spectral density. Basically, the importance for that is it avoids a particular singularity at the origin, but not for our purposes all that important. So just sort of setting us up for the sake of simulation, how do I want to sample a random phase screen, right? So if I have my medium modeled as the mean index plus some sort of random fluctuation, I want to generate this random fluctuation. Of course, I could do the autocorrelation function, but of course, I just told you that I don't know the autocorrelation function. So I go with the power spectral density. So what I can do is from the power spectral density, we'll walk through this a bit more carefully in a bit. I can draw random samples on a computer. So now let me actually show you how a wave would be affected by turbulence. Okay, so let's say I have a plane wave on the left. It's going to be moving to the right in a minute here, and then it's going to get dented up by the atmosphere. I can go back and forth through this animation a couple times. So basically, at each slice, there's going to be an instantaneous atmospheric slice. Okay, that will be the little video in the bottom right. So each slice is going to have a almost unique slice. They'll be correlated, of course, along the propagation direction. But for the most part, let's just assume, because I have a discrete amount of samples here, that they're sort of uncorrelated, independent. So if I move this, my instantaneous atmospheric slices will add up into that plane wave. They'll sort of start to distort the plane wave. And eventually, they'll all accumulate until at the very end where I hit my aperture, I've accumulated all of this sort of denting up from the atmosphere. And then you can see this point spread function, okay? So what this is going to be is it's the same thing as last time. It's just the Fourier transform of a circle, but now it's not only just a circle, it's a circle with this dented up pattern in it. So it's this denting up that's really going to do the damage to my point spread function. And on the right here, I just have a GIF. I think there's a bigger version of it later, where I have some what we call like random phase realizations. Okay, so basically, what does the wave look like after it went through the turbulence, and then the resulting point spread functions, and they're increasing in turbulence strength from left to right. So basically, the important equation for us is going to be that the resultant phase that the wave will have after propagating through a turbulent medium will be this equation, effectively just adding up all the distortions along the way, right? Integrating along the propagation path, adding up the distortions. So let's say I wanted to generate a random field, okay? Because obviously at some point I have to generate a random field if I want to simulate this. How do I do that? Okay, so basically what I do is I have my power spectral density kernel. I'll multiply it by a little bit of, in truth, complex white noise, but I just say white noise here. And then I'll take the inverse Fourier transform basically of those two things. And in truth, it's the square root of the power spectral density. So this is going to be really the way that we end up doing kind of all the simulations later. Since we know the power spectral density, we'll take the square root of that, multiply it by the Fourier transform of the white noise, and then take the inverse Fourier transform of that. We end up getting some output random field. And to prove to you that that works, here's, I think, maybe just 100 random realizations averaged. So I have a theoretical, this is a covariance correlation curve. But you can see that the empirical matches the theoretical pretty well, with the exception of some of the finer bits at the end there. So really, we'll just end up using those power spectral densities, the Kolmogorov power spectral density or the von Karman power spectral density, multiplying it by white noise. There you go. So let's talk about a bit more about some of the specifics of some of these terms, okay? CN squared and these things. First thing that we want to talk about is why is there no autocorrelation function, all right? So he assumes that the turbulence effects are non-stationary, which then sort of makes the autocorrelation function, you sort of have to make a philosophical decision at some point, which is what do I consider a random fluctuation and what do I consider as a deterministic fluctuation? So here's the following example. If I just consider like this little scene here, okay? In the daytime, it's going to be hot. It's basically going to translate to more fluctuations in the index of refraction. But as the day cools off, cools down, and it becomes nighttime, these fluctuations are going to drop along with the temperature, right? So this mean value is clearly moving, okay? Now, is this a random fluctuation? Is this a, sort of more of a ish deterministic fluctuation? This is kind of maybe a philosophical question, okay? And not only do you have to consider for this situation, but all kinds of situations. So Kolmogorov says, I don't want to think about that. I'll invent a new thing instead of the autocorrelation function, which will sort of be a reference-free way of measuring how 2 points are related. So he calls this the structure function. So you can see that the mean value will be canceled out. For things that are close together, the mean value will be canceled out. So then he doesn't even have to think about this question. He sort of just eliminates it by default. They're actually end up going to be very similar. I don't think we have a slide about this, but we can still use the power spectral density and sort of a very similar like Wiener-Khinchin theorem to describe the relationship between the structure function and the power spectral density. So there's a very close link relationship between the two things. But really what the autocorrelation function does is if two things are very similar, right, it'll be like, let's say a large value. Whereas with a structure function, if two things are very similar, it'll be a very small value. So it's kind of just like the opposite in some sense of what you're typically used to. So here's what the structure function ends up being. It's CN squared multiplied by basically just some sort of displacement in space. So if I know that my medium, my turbulent medium, is described by this sort of statistical property, and I propagate a wave through it, it isn't too unreasonable to expect that the wave sort of inherits this statistical property as well. There is a slide about, a couple of slides in the bonus slides about exactly why it ends up being this way, but I don't think it's too unreasonable to say if I'm propagating a plane wave through a medium with some property, it will sort of inherit that property by virtue of the wave propagation. So what we'll end up seeing is not only do the indices of refraction have a structure function, but the phase itself, the phase error that ends up being at my imaging system also has a structure function. And here we have a plot of CN square varying with altitude. Okay, so if I'm looking up at a star, the turbulence intensity strength is going to be much less at the higher up that you're looking. And that makes sense because there's just simply less air up there, less atmosphere up there. So there's sort of less to dent up the wave. Okay, here are a couple examples of CN squared. These are real CN squared profiles. The Huffnagle Valley profile, submarine laser communication day profile. So you can actually measure these things, and maybe this sort of gives you a sense of the ranges at which we're talking about. Again, you can see that they're pretty small, 10 to the power of -14, 15, 16 for the most part. At most elevations, they're going to be in that range. So let's sort of take a simpler perspective of these CN squared profiles. If I'm looking vertically, as we said, it's going to sort of decay the further up from the ground that I get. However, if I'm looking at a horizontal path, it'll be almost constant. This might change, say, if you have like a fire in the way or something like that. Of course, that's kind of a silly example, but like a road will emit more heat than maybe a patch of grass. So it doesn't have to be necessarily exactly perfectly constant for a horizontal path, but to a decent approximation, it can be constant. However, there can be some fluctuations due to some sources like this. But all of these can be modeled, these fluctuations, and be put into the phase function. So with more turbulence strength, with more CN squared along the path, my wave ends up becoming more dented. And as you can see in this picture here, that the more dented my phase function ends up being, the worse my point spread function ends up looking. So how do I actually how do I go from this to this? How do I go from the phase to the point spread function? All I do is just the Fourier transform of the phase error, okay? So it's almost like what we did before, where it was the Fourier transform of maybe just a circle, but this time it's going to be a Fourier transform of a circle with some extra complex error to it. We'll take the magnitude square of that, and then I'll get my point spread function. This is, of course, assuming incoherent imaging. Okay. One of the most important quantities in sort of the turbulence literature is the Fried parameter. This is the expression for the Fried parameter, but I think that's kind of not very clear as far as what it means. So here's maybe more of an intuitive definition. For one, a large Fried parameter is going to be low turbulence. A small Fried parameter is going to correspond to high turbulence. And we typically write D over R naught as our sort of measure of turbulence strength. But let me give you a sense as to why that is. So let's say I have a very small Fried parameter. The Fried parameter is basically quantifying how big is the average flat region of the wave, okay? So let's say the wave is very flat, okay? Let's say it's basically a plane, okay? That's as flat as you can get, all right? The Fried parameter is going to be huge. So if I look at my aperture size and I think how many Fried parameters, or how much Fried length can I fit into my aperture? In the case of a plane wave, it's going to be, the Fried parameter will be way bigger than the aperture, which will correspond to a flat phase error over the aperture. However, if I have a very dented up wave, I'll only be able to draw very small circles on the wave front. Therefore, I can fit actually a bunch of Fried parameters into the aperture. And in this case, that will correspond to a very dented up wave front, okay? So you can only imagine these little areas as being flat. And of course, across the whole entire aperture, that's going to correspond to a pretty great deal of wavefront error. So it's sort of a way of quantifying turbulence strength. So how strong is the turbulence? It's typically measured, as I said, in terms of D over R naught, with no turbulence being under 1, moderate turbulence being between 1 and 4, and strong turbulence being over 5. You can see this scale right here. This is basically going to be, I think, yeah, this is the end of, I think, my half, right? I think so. So, so now we're going to move into split step propagation, simulation, all these things. So, all right, thank you.
Okay, so what are we going to do next? So far we have gone through a lot of college physics, right? Some optics, how do wave propagate. What are we going to do next? Well, eventually we want to do these on computers, right? We want to train deep neural networks to recover images. But the first thing to do to train a network, what do you need? Data. Where do you get the data? Well, I go outdoor and take a picture. Great. How many pictures can you take? That's one question. The other question is, where is the ground truth? You take a picture on a hot day, you say, okay, I'm going to wait until night. Well, then the light changes, right? So how can you get a ground truth? Taking real data is extremely hard for turbulence. So you need to synthesize. So how can you kind of synthesize? Well, you're going to have some kind of simulator on computer, right? So that's why we want to go through this part. How do we simulate turbulence? What are the mainstream methods, and what can we do to speed them up? To give you an idea, those mainstream methods, we are talking about half an hour to an hour for an image. Okay, so you can do some mental calculation. Half an hour for an image, okay, of a certain resolution. Typically, you train a network, how many images do you need? You sort of know, okay? 1,000 videos, 100 frames per video, that is the number. Times how many minutes per frame, that would be the amount of time you need to generate the training data. Okay, so we're going to show you some of our latest work on how do we simulate these in real time. Real time and without any interpolation. By the way, most of these standard methods, they are interpolating. They have agreed the points and then they interpolate. So we can do it without any interpolation. Okay, so to get started with, let me talk about this mainstream method. It's called a split step propagation. Okay, so if you search literature on turbulence simulation, that would be the term to look for, split step propagation. The concept is as follows. You go for every point in the object plane, okay? Every single point in the object plane. You slice your propagation path into many, many, many segments. Each segment, you can imagine that it is a funny lens, okay? And by lens, I mean that the refractive index is changing, okay? So for every slice, you have a lens with some kind of refractive index. And therefore, as the wave goes from one point, the entrance, to the other point, the exit, the phase is going to change. Sometimes it will go faster, sometimes it will go slower because of the refractive index. Okay, and so now you're following me, right? One point in the object plane, many, many slides. For every point, you need to do some calculation. Now, what is that calculation? It's called the Fresnel or Fraunhofer diffraction. And here we are using the Fresnel diffraction, right? You remember, we take that point, look at its neighborhood, we take a Fourier transform, and then we add some additional Gaussian phase terms to alter it. That complicated equation that we go over in part one, right? So that is equation, that equation is applied to every point in every segment. That is the amount of calculation, okay? But if you manage to do it, then what you can see is that here you have a couple terms, point going through this, what we call the phase screen. The phase screen is just the exponential to the power j 2 pi, and that's a phase term. Now, if you're still not following, what is the phase term? The phase term is something that we can draw from the power spectral density. Okay, so that's undergraduate probability. So if I tell you the power spectral density, there is a way to draw the random realization. So I can do that. And that power spectral density is called a Kolmogorov power spectral density. There's an equation to that. So I can draw that, and then I can apply the phase. Now, look at this picture here. I'm not using the entire phase. I'm not using the entire phase screen because I'm actually quite close to the object plane. Okay. Now, as I am moving farther and farther away from the object plane, that thing becomes bigger and bigger. Okay. So the neighborhood size, or how many pixels that I need to do the Fresnel propagation changes along the path. As you are looking at the image plane, you are seeing some funny thing. That is the phase. The event. Eventually, what is the phase that you're seeing in the image plane? And then you can take the Fourier transform of the exponential, take the magnitude square and something like that. Then you can see this is the point spread function. That's changing over time. Okay. If you don't have this turbulent layers, it will just be what we call it the airy disk. So that's a diffraction limit blur. Okay, so the elements of split snap, as you can see here, we need to generate the random phase screen. Then we need to do the numerical wave propagation, and then you do the image formation. So what is a phase screen? As I mentioned, a phase screen is just the random realization, okay, of the power spectral density. And so as the wave is propagating through this random media, you look at different segments of this phase screen. So you have many, many phase screens along the path. Now you may ask, how many phase screens do I need to model the turbulence? That depends on how far you are and how bad the weather is. If you have a very bad weather, your path is really long, then you need to have a lot of segments in order to model it appropriately. Especially we have something funny in the middle of your path. You put a fire in the middle of the path, then of course you need to have a phase screen to model that. Okay, so this is an animation that Nick has shown you before. And to give you a sense of the effects of the propagation path, in this slide, we're showing you as the propagation path grows, the point spread function that you're seeing is going to go. Okay, so from point source to aperture plane, without any turbulence, it will have this kind of shape. Now, what will happen if you have a turbulence? Then what you will see is that with turbulence, these kind of point spread functions, you will start to see the shape. Okay, it will start to distort. And this is another figure showing you that this is the phase that you can draw, and then you form this equation, then you can get the point spread function. Okay, so why is this hard? Of course, it's taking, you have a lot of segments. You need to do it for every point. One thing that is very, very important in turbulence simulation is that you want to ensure one point in the space is correlated to another point in the space. Now, if you don't care about that, it's very easy. Well, just draw the IID Gaussian random perturbation of the pixels. Right? What I mean is that you look at this pixel, oh, okay, go to that location. Right? So that's a random perturbation. You shift the pixel to a random location. You do it all independently. That's not turbulence. Turbulence says that if I have one pixel here, if I'm looking at a pixel right next to it, it should experience something very similar. And in fact, it has certain kind of distance, spatial distance, for a region of pixels within this image. They should share some kind of same or similar direction of movement. Right? So if one point is shifted to the top right, then another pixel should also shift to the top right. Okay, and that should have some kind of, we call it a range of correlation. This kind of spatial correlation is maintained by this split step propagation. The reason is that as you are propagating through this path, remember that circle becomes bigger and bigger, right? The circle becomes bigger, and eventually they will overlap. that kind of growth and overlap will give you the correlation. Why? Because let's say you have 2 points, they start to overlap, okay? And that means the 2 points, you think about those 2 circles, you have overlapped regions, right? Those the random realizations, they are shared by 2 points. And so if the 2 points are very close, then you overlap more, then you have more correlation. 2 points that are really far away, you don't overlap, you don't have correlation. So that kind of spatial correlation is maintained by split step propagation. And therefore, you really need to propagate. That's taking you a lot of time. Okay, okay, so this is a simulation animation showing you how we're going to do the split step. And you can see that this is a real simulation by our computer. For every point in the scene, you get a different point spread function. So in terms of image formation, deblurring, that kind of purpose, you should really think about every pixel in my image is experiencing a different blur. That's very hard, okay? On top of that, every pixel will also go to a different location because of the phase. Okay, so now you have 2 effects. You're moving to a different location and you're experiencing a different blur. If you ever have done image deconvolution, the blind deconvolution, you will feel this is already pretty hard, right? You need to estimate the image and you also need to estimate the blur. And usually that's so hard that you sort of do it alternatingly. In turbulence, the inverse problem is even worse because you need to estimate all the point spread functions, which is almost impossible. On top of that, you also need to estimate all the displacements. And so we don't have a perfect solution here, but you can see the difficulty. Now, even before we talk about that inverse problem, just forward process, how do you get to those pixel shifts and also the blur? That is not trivial. So implementing the split step is not fun. We spend quite a bit of time, a year or 2, to just learn how to reproduce the results in the literature. In fact, the numerical approach in simulating the split step, the documentations we can find from the books. However, the actual code, most of them, they're proprietary. So there isn't any open source code. So we managed to build it's open source right now, split step. So we can build it. It's difficult. It's difficult. It takes a lot of time. Now, there are alternative ways to do the propagation. You can do ray tracing. So I know in computer vision, we're more familiar with ray tracing techniques for graphics rendering. You can do that. However, for imaging through turbulence, the complexity, in my opinion, it will be similar. Because for ray tracing, if you know anything about ray tracing, you need to know the environment. You need to know where the wave is coming from. You sort of need to know the geometry of your room. For turbulence, you're talking about long range, you really need to know where the buildings are, where the trees are. You need to know those. Those are very difficult to measure. So that is the difficulty. You can also do the, I know we like GAN, right? Generative adversarial network, really, really like GAN. GAN has some limitations because the generalization is always an issue. You also sort of give up the physics-based rendering. So that's also another drawback if you go purely with a GAN without thinking about the physics. So if you read the literature, you will probably see some work, especially in applied math, in image processing, transactions on image processing, PAMI, those literature. You will see about 10 years ago, 20 years ago, we have a lot of models for turbulence. They're mostly what I call a zero-order approximation. So what they do is that, okay, I have an image, and then I assume that there is a grid. And then I will assume that there is a deformable deformation of the grid. So that would tell me the pixel shift. And then I will apply a Gaussian blur to the image, right? So that's what I call a zero-order approximation. That's a good approximation if you think from the split step propagation side, right? Eventually, it will just be the pixel shift, and then you have a blur. So that sort of capture the essence. But when the turbulence strength becomes stronger and stronger, propagation path becomes longer and longer, the zero fault approximation will have a problem. It doesn't really capture the scene. And later on, I can show you that if you use this kind of approximation to generate training data, to train your network, it's going to perform worse than if you're using a really powerful simulator to synthesize the data. So the simulator actually matters quite a bit in this game. Okay, so what I want to do is to talk about a simulator, what I call the propagation-free simulator. That is the work that Nick and I have been building. We're still working on that. We've gone through how many versions? This is right now it's version 4. What I'm going to show you will be version 1 and 2. It will be a bit easier to understand. Propagation-free. Why do we need that? The reason is split stamp is just too small. Okay, too much work. So how can we do propagation-free, and what will be the benefit? The ultimate benefit is that we can do it real time because you do not need to propagate anymore. So how do you do that? Well, the biggest concept is to collapse. Okay, you start with a lot of phase screens. You just collapse them, squeeze them together. Now you ask, oh, why can you do that? Didn't you just tell me that I need to propagate through all these layers? How can you collapse them? Well, the reason is, if ultimately what you care is how many pixels that you have shift and how much blur are you there, if I have a mechanism to tell you these two pieces of information, you don't really have to go back and then do this overlapping circles and then propagating through the Fresnel, because what you have been doing so far is to really use that kind of propagation mechanism to tell you the correlation and then the blur, and so the what we call the tilt, right? Pixel shift. If I can directly give you that piece of information, you can skip all the propagation. So that's our goal. So how do we collapse? You look at 2 points in this example, right? Point 1 and point 2. Ultimately, what will affect your pixel is that phase function, right? Every phase will give you a point spread function, and the point spread function will be applied to your image to give you the distortion. So if I know at every point, let's say I'm looking at this point, I know what will be the effective phase function, problem solved, right? I can just get the point spread function, I can blur it. So all I need to know is to know the phase at this point and need to know the phase at this point. So these are the 2 things I need to know. So let's see how we can do that. Here is the phase, right? So here's what we call it the collapsed phase screen. Look at 2 points, you have the local phase. Okay, so these are the 2 phase functions. And I can apply this formula, take the Fourier transform of the exponential, take the magnitude square, I can get a PSF, point spread function. Then I can start to do the blur. So how can I get the phase function? Well, you need to draw from the Kolmogorov power spectral density, sure. But if you only draw them independently, that doesn't solve the problem, because I still need to maintain that the 2 points in the space, they're correlated. So the correlation is the key. What can I do? Well, I can go to a representation space. This is a little bit advanced. So every function can be written as a set of basis functions. Okay, every function can be written as a sum of basis functions. The phase function that I'm looking at is a circular function. They're defined on unit circles. And therefore, the basis function, they also have to be defined on the circles. And the basis function I'm using, they're called the Zernike polynomial. So if you read any optics textbook, you should be able to see this term. Or some people, they call it the Zernike polynomials. So you get these Zernike bases. They're orthogonal to each other. And so they sort of form the good set of bases. And so you look at this phase. Phase can be written as all these bases. Now these bases, they are predefined. Zernike defined it, okay, long time ago. So we don't have to worry about that equation. AJs, these are the Zernike coefficients, right? Zernike coefficients. So if I want to give you this phase function, I need to know the coefficients. Okay, so here's the game. I look at one point in the image. I look at another point in the image, right? For the first point, I have a set of Zernike coefficients. For the second point, I have another set of Zernike coefficients. I want to maintain the spatial correlation between these 2 points, and therefore I need to maintain the spatial correlation between the 2 vectors of Zernike coefficients. Following, right? So if I know the correlation between these 2 vectors, I'm done. Right? So that is the goal. It turns out that this question has not been answered in optics. I can explain why, because in optics, at least for the development of turbulence, is mostly about point source, optical communication, right? So you want to transmit something to the satellite to you, 1 point, right? Look at star astronomy is 1 point. We sort of not do much on horizontal imaging, where you have a camera, you buy the Canon camera, you have wide field of view, and you're looking at buildings, and then you're looking at cars, and you're looking at license plates, people. You sort of don't do that in astronomical imaging. So that correlation is not really studied in the literature. So we need to do some work. So let me skip some of these slides for the sake of time. In the past, what we know is another correlation. Okay, this correlation is useful. I will come back to the spatial correlation in 2 seconds. This correlation is done by Robert Noel. He says that, ladies and gentlemen, you have a vector of Zernike coefficients. These Zernike coefficients, they have correlations. Okay, so let's say you are looking at the 36 Zernike coefficients, Zernike coefficient 1, 2, and 3, right? So you have a set of basis functions. They each have a coefficient. They will have some kind of correlation. We call them the intermodal correlation. That is well defined back in 1976. Okay, so that is the correlation between 2 Zernike coefficients. So that we know. However, what we don't know is 2 points in the space. 2 points in the space that we don't know. So we went back to the literature and we find one thing that's very useful. Although people haven't really studied the correlation between 2 points, right, 2 spatial points, they have actually built multiple telescopes. Okay, so think about that. Now, of course, we are taking 1 camera, look at 2 points in the scene. In astronomy, they have 2 cameras looking at 1 star. Okay, now you say, okay, why are they related? Have some imagination. The 2 telescopes looking at 1 star, flip it over, right? Optics, right? Flip it over. Then you have 1 camera looking at 2 points. Okay, so you can do this mirroring technique, and we can prove that kind of mirroring technique will work. Then you can go back to this paper. This is by Gary Channon. So what he says is that if I have 2 telescopes looking at 1 point, I can calculate the correlation between these 2 apertures. Now, they need to do that because they're looking at really, really tiny stars, and 1 aperture is not enough to capture the star. So they need to have 2 apertures. And so they need to calculate the correlation between 1 aperture and the other aperture. They call it the multi-aperture. We sort of flip this over. We say 1 camera look at 2 points in the scene, and that is an equivalent relationship. We can prove that. Once we do that, then what you need to do is to really just use the Gary Channon equation, and with some modification, then you can apply it to our case. Then you can get back the correlation between 2 points in the scene. So if you go to this paper, you will be able to see more derivations, but the overall idea is to flip it over. Then, of course, Gary Channon and also some follow-up work, they have given us the foundation to do all this simulation. The equations, they are not too long, about 1 page. Okay, just to implement that thing is about 1 page, including all the 36 Zernike coefficients, and then you have different modes. It's not too long. Okay, that long. Okay, so we implement that. It turns out that is very fast. Okay, why? Because compared to split step propagation that you need to do this every segment for every point. Now you just need to go to the image. You just start off by drawing all these Zernike coefficients in a correlated way, right? So the way we do it is that we know the correlation. We have a formula. Is that long? Fine. We implement it on computer. The equation is long, but then the computation is very short. You know, okay. So that's sort of funny, right? Sometimes when you train deep neural networks, the code is pretty short, but it takes forever. Right? So here is the opposite. The equation is very, very long, but then the implementation is easy. So we do that. So we have, what do we have? Well, we have all the correlation. We stored it in the power spectral density. We store everything there. And then you start to give me a white noise vector, and then I generate all these random fields. I can give you the correlated Zernike coefficients. I give you all these, then you get a PSF immediately, right? So that is the speed up. To just give you a feeling of how well we can do, here is a split step propagation. This is our simulation. This is our tilt map. Is the pixel displacement map. Using my eye, I can say they're similar. But you know, it's always impossible to compare apple to apple because these two images, they are generated using two different random visualizations. It is impossible to get the exact same match, okay? Just because the two mechanisms are completely different. We can do some kind of evaluation that is called the Z-tilt and the T-tilt statistics. So if you ever do turbulence simulation, people ask, how do you verify? These will be the standard things to verify. So these are the expectation of the two directions. So you need to look at those. And that's why I always have questions about these GAN type, that kind of work, because yeah, the images, they look decent. They look decently blurred, distorted, but then if you want to track these two statistics, it will be harder to verify whether the two statistics are maintained by the GAN. Speed-wise, we are getting about 20 to 30 times faster. Not too much, but it's still a huge improvement. And that actually gives a lot of room for further improvement. Okay, so time's running short. So let me also tell you another big thing that we did to really speed up so that we are approaching real time. So the difficulty of that one was a version 1 simulator is that drawing the Zernike coefficients, that's not hard, okay? Because now we have a long formula, but we just click a button, we can get out those. The hard part is that you need to get the point spread functions. You say, oh, wait. Don't you just have a formula, right? The H equals to Fourier transform that phase. Don't you have a formula? Yeah, you have a formula, but you need to apply this formula for every point in your scene. Okay, and so you still have the number of pixels, million pixels in your image. You need to do million equations of that. That is going to take forever. So that's one. Another source of problem is that you need to blur. You need to blur your image using the point spread function. And now how many point spread functions do you have? You have a million of those. Then you need to blur them one by one. That is going to take forever as well, right? So how am I going to do that? It's the same idea. It's called the basis expansion. So for every point spread function, I can write it as a sum of bases. Now don't confuse. Okay, this is the basis function for the point spread function in the spatial domain. The basis function I was talking before, it was the basis function for the phase in the Zernike domain. Those are the two different things. There is a relationship going from the Zernike coefficient to the spatial coefficient, right? So the Zernike, I call it the AJs. Here I call it the betas. There's a mapping from that to that. Okay. There is a mapping, I know, but we are not able to prove it. We're not able to derive it. I'm going to show you how we can manage that. But once we can overcome that issue, then what you will end up having is very easy. Instead of blurring through each individual point spread functions, you just blur through these 100. In our case, it will be 100 of these bases. That kind of convolution is very easy. Okay, let me show you how. You start with an image. You blur the image by these 100 basis functions instead of the 1 million points per functions. Blur your image with these 100 basis functions. So you can pre-compute it. And then for every point, every pixel in your image, you have a different coefficient. Okay. Now, of course, we need to have a mechanism to generate that. But imagine that we have generated those coefficients. Then it will just be the pixel-wise summation of all these individually blurred images. You add them up, we can get the distorted image. So here is the magic. Okay. How do you do that mapping from the Zernike AJs, okay, Zernike coefficients in the phase domain, in the Zernike domain, to the basis functions in the spatial domain? And I said, Nick and I spend a lot of time, we are not able to derive the equation. It's just too complicated. So thanks to the invention of deep neural networks, so problem solved. And now how do we solve it? We use a neural network to do that kind of mapping. Oh, you're cheating. You said you're going to teach me physics-based rendering, and then you're not doing neural network. Oh, yeah. It's not a deep neural network. It's actually a pretty shallow network. So that network is implemented by another student, Xuan. So he said, okay, the input, we just need 34 coefficients. The output is 100 coefficients, fully connected. How many layers? 3 layers. Okay, train that thing. After you train that thing, you will have a mapping. It turns out that this mapping is pretty good. It's pretty good. Okay. How do we train that? Well, you have some training data. You have the Zernike coefficients we can generate beforehand, and then we have some basis coefficients we can sort of pre-calculate. We generate 1 million of those. We just train this network. A very small, very shallow network, and you can parallelize this network easily. Put it into the simulator. So then you have a entire thing, right? So the entire thing would be that I look at the image, okay, and then I look at the power spectral density. I sort of pre-compute the power spectral density, draw the random field, okay, and then for every random field I have in the scene, I run this phase-to-space transform. It's called phase-to-space is because you're going from the Zernike space, that's a phase space, to the spatial domain, that's the spatial space, right? So phase-to-space, I do this transform, which is a network. Then I can map the Zernikes to the spatial domain coefficients. Once you have that, then you go back one diagram here, you do the basis convolution, pixel-wise summation, done, okay? That is going to give you 1,000 times speed up compared to the split snap propagation. And all the statistics, they are maintained. To give you an idea how fast it is, we can go from half an hour, 10 to 20 minutes per frame, down to less than 1 second per frame. So you're talking about how many, we did a calculation of certain kind of resolution, forget. It's pretty astronomical figure. It's about 100 years to train one data set. We can go down to a couple hours to train to get a data set. So that is the scale that we are able to achieve. So you can get this simulator. I will skip some of these pictures. You can get the simulator from our website. So this is a sort of the baby version of the simulator. It's a little bit constrained to certain resolution, to some configurations, but I think is okay. It's okay for a lot of experiments. Okay, so you can do that. To give you an idea, the speed, the split step, this is the reported time in the literature. GPU, 24 seconds per frame. We are doing 0.026 seconds per frame. So that sort of really opened the room for a lot of neural network studies. Okay, this is a pretty meaningful experiment to share with you. Okay, why is a simulator important? Here, the experiment is done on on 2 different simulators, this new simulator and also another simulator by using the 0th order approximation. And we use the exactly the same network architecture, exactly the same ground truth image, just train them using 2 different simulators to simulate the turbulent effect. The outcome is quite significant in terms of PSNR. Okay, the performance using a better simulator compared to the results using a worse simulator in terms of image reconstruction, several almost 1 dB difference. So you can see that has an impact. Okay, so to just summarize for this part, and then we can take a break. We've gone through the wave propagating through turbulence. The key message here is that just think about turbulence as a funny lens. Okay, the index of refraction is changing along the path. That is going to distort the phase. Message 1. Message 2 is that the index of refraction of phase is given by this equation. So you have index of refraction, that's n. Just integrate along the path. That would be the phase function. And you can draw that random realization according to the Kolmogorov power spectral density. So that's message number 2. Message 3, if you do incoherent imaging, then you can get the points per function according to this equation. Message 4, that is the basis representation. That's any key. 5, split step. It is the gold standard. Propagating through, maintain everything you want, slow. 6, you can do this multi-aperture technique. That's version 1 simulator that you collapse everything down to a single screen. The last message is that you can do this kind of spatial domain approximation using a shallow network. Here is an animation that my student Juan he made. It's a very beautiful simulation. It's a real time, okay, real time. So this is not a. You can hook up a webcam. You can hook up a webcam, and we can do the same. Hook up a webcam. Look at the scene. This is about 7 to 8 frames per second. Resolution, this is 512 by 512. And we're doing this for dense grid, no interpolation at all. Okay. And here you can see the instantaneous points per function that is real-time generated. And you can look at the tilt statistics. We're comparing to the theoretically predicted by the physics. So what should they look like, and what would be instantaneous? The tilt statistics. The instantaneous tilt map we can also show you right on this GUI. Okay, so if you want to get access to this, contact me. This has a pending IP application. But for research purpose, if you just want to get a hold of our baby version, just get a feeling of what it looks like, you can just go to our website and download that Python code, and you can use that. Okay, so let's take a break. Let's take a break for another 10 minutes, and then we will come back at 11:10, and then I will talk about the exciting things, how to recover images. Thank you.